Hey, if you can, we have some notes on section 7.8 through 7.10. And this kind of talks about equilibrium, comparing the reaction quotient Q to K to see if a system is at equilibrium and how a system will proceed in terms of the reaction. So here we have an example regarding the reaction quotient. So remember, the reaction quotient and the equilibrium constant, they have the same setup. You calculate them the same way. It's just the reaction quotient you can measure at any point in the reaction, whereas the equilibrium constant is only at equilibrium. So by comparing the two, we can figure out if a system is at equilibrium or not. So here we have an example with sulfur dioxide and chlorine gas reacting to make SO2Cl2. Our equilibrium constant is 0.042 at 227 degrees Celsius for this reaction. A chemist tests this system and finds these concentration values at a given time. So a concentration of sulfur dioxide is 4.62 times 10 to the negative 4 molar. Chlorine gas is 3.85 times 10 to the negative 3 molar. And SO2Cl2 is 2.78 times 10 to the negative 5 molar. So the first question is this system at equilibrium? And if it's not at equilibrium, which direction will it proceed? Meaning, will the forward reaction take place more or the reverse reaction? So when we write Q, we're not sure if the system's at equilibrium or not. It may or may not be. So we have to figure out if it is by comparing it to K. Remember, the system is at equilibrium if Q equals K. So here we have a reaction quotient, again, used to determine if it will proceed or if it's at equilibrium. So QC is equal to the concentration of the products over the concentration of the reactants, raised to their stoichiometric coefficients. And we get a QC value of 15.6. In the beginning of the problem, they gave us a KC value of 0.042. So since Q is greater than K, we know that the system's not at equilibrium because they're not equal. And we also know that the system has too many products to be at equilibrium. So the reaction will proceed to the left, or the reverse reaction will proceed more than the forward reaction until the system establishes equilibrium. So again, here's our equation. We say that the reaction proceeds in this direction to the left, or the reverse reaction proceeds until equilibrium is achieved. So the concentration of SO2 and Cl2 will increase, and the concentration of SO2Cl2 will decrease until the system reaches equilibrium. So here is a slide comparing what it means when Q has different values. So if Q is greater than K, as we just saw, the reaction will proceed to the left, producing more reactants, and it will continue to increase the concentration of reactants until equilibrium is established. If Q is less than K, the reaction will proceed to the right. It will continue to increase the concentration of products until equilibrium is established. If Q equals K, we know that the system is at equilibrium, so both reactions are occurring at the same rate. Okay, so remember, if Q is greater than K, that means the concentration of the numerator, or products, is larger than that of the denominator. And if Q is less than K, that means the numerator is less than that of the denominator. So that means that there are more reactants than products, so more products will be produced. Here is Le Chatelier's principle, which basically states that when a system is at equilibrium, if you change something, which they call subjecting to a stress, the equilibrium will shift in some way to reduce that stress. So equilibrium is a happy place, and basically the system is trying to always go back to that equilibrium state. So there are three stresses, which include pressure, concentration, and temperature, that one might change in order to shift equilibrium. So from increasing pressure, if the pressure on a system at equilibrium is increased, the Q will change and the reaction will proceed toward the side with fewer moles of gas to reduce that stress. Okay, so fewer moles of gas means a lower pressure. Remember, pressure and moles are directly related. So if you increase that pressure, what's going to happen is the system is going to try to then decrease the pressure by decreasing the number of moles of gas to reduce that stress. So when equilibrium is reestablished, Q will equal K once again. So this changes the equilibrium concentrations, but does not change the equilibrium constant. Remember, the constant is a relationship between a numerator and denominator, products and reactants. So those concentrations might change, but the overall value does not change. It's kind of like how 1/2 equals 2/4. Even though the numerator and denominator aren't the same, they both equal the same value, 0.5. So here we have 14 moles of gaseous molecules, and then here we have 10 moles or particles of gaseous molecules. So when we increase the pressure, the product side has fewer moles than the reactant side, so the reaction will proceed that way. So here, again, we have 14 gaseous molecules, 2 NH3, 5 N2, and 7 H2. And then when we decrease the pressure, the reaction proceeds towards the products because there are fewer moles of gas on the product side, so that we have 6 NH3, 3 N2, and 1 H2. So notice that we have more particles of NH3 once the pressure is increased on the system, but the particles of N2 and H2 decrease. If we decrease the pressure on the system, that's also a stress. So the Q will again change and the reaction will proceed toward the side with more moles of gas to reduce that stress. So if we decrease pressure, the system is going to want to increase that pressure back to equilibrium. So it's going to go towards the part of the reaction that has more moles of gas, because again, moles and pressure are directly related. When equilibrium is reestablished, Q equals KEQ again. It changes the equilibrium concentrations, but does not change the equilibrium constant, KEQ. So here we have increased the pressure. It's the same equation that we use to compare decreasing pressure, but this time the reaction proceeds toward the reactant side. So on the reactant side, we have 4 moles of gas versus the product side having only 2 moles of gas. So that's where we go towards the reactants. There are 10 gaseous molecules again and 14 gaseous molecules if we were to go the other way. We can also introduce a stress by changing concentration. So if we increase the concentration of one species in the equation, Q changes and the reaction will proceed in the direction that will reduce the concentration of that species. So it's kind of like if you input more reactants, you're going to get more products. If you put in more products, you're going to get more reactants. So once equilibrium is reestablished, Q equals KEQ once again. Again, it changes the equilibrium concentrations, but does not change the equilibrium constant, KEQ. So here we have the same equation, N2 plus 3H2, yielding 2 NH3. At equilibrium, on the far left here, we have 1 NH3 molecule, 1 N2 molecule, and 3 H2 molecules. If we add NH3, the system's no longer at equilibrium. I gotta move my thing, sorry. There we go. The system's no longer at equilibrium. We increase the number of products, so the reaction is going to go towards reactants. To achieve equilibrium once more, there are now 4 NH3, 2 N2s, and 6 H2s. So if you find the equilibrium constant, you will notice it will be the same for here, the far reaction, and the far left reaction. The KEQ will be the same even though the concentrations of all the species are different. We can also introduce a stress by decreasing concentration. It's basically going to have the opposite effect. If we decrease the concentration of something, the reaction will proceed to increase the concentration of that species. Same idea, Q equals KQ again at equilibrium. And even though there's going to be a decrease in equilibrium concentrations, it does not change the equilibrium constant, KEQ. So here again, we have a system this time with 11 NH3, 4 N2, and 12 HQ at equilibrium. If we remove 7 NH3s, we now have 4 NH3, 4 N2, and 12 H2, and we're no longer at equilibrium. The reaction will proceed to produce more NH3, so that now we have 6 NH3, 3 N2, and 9 H2. We can also introduce a stress by diluting. So remember, diluting something is going to reduce that concentration. If a solvent is added to a system at equilibrium, so for example, we add water to something, Q will change and the reaction will proceed to the side with more particles to basically increase the concentration once more to reduce that stress. When equilibrium is reestablished, Q equals KEQ once again. Concentrations change, but the equilibrium constant does not change. So here, if we have 13 aqueous HF, if we dilute it, we get 8 aqueous HF. Looking at the reaction, there are more particles on the product side than there is in the reactant side. So we're going to proceed towards the product side because there are 2 moles of aqueous particles versus 1 mole on the reactant side. Temperature can also introduce a stress to a system, and it's the only stress that will actually change the value of the equilibrium constant. So a lot of times in science, constants are specific to a certain temperature, so it makes sense that the equilibrium constant would be different if we change the temperature. So this all is going to determine whether a reaction is endothermic or exothermic, whether or not it takes in heat or releases heat. So sometimes you will see a reaction where they put heat either on the product side or the reactant side. But another way, and a more common way you'll see these problems introduced is with a delta H value. Okay, so if we cool a system, it's going to shift the equilibrium in the direction that produces heat. So it's kind of like it's trying to bring that temperature back to what it was. If we add heat something up, it's going to shift to the equilibrium in the direction that absorbs heat. So here we have heat on the product side. If we take away heat, we're going to go in the direction that produces heat, so we're going to go towards products. But if we add heat, it's going to want to remove that heat, so it is going to go towards the reactants. So here we have a system represented by the chemical equation below in a state of equilibrium at 25 Celsius. Describe the color change that would occur if the temperature increases to 75 Celsius. Okay, and this is what I was talking about with the delta H value. Typically, they don't put heat in the equation. They'll give you a delta H value, and you have to interpret what that means. So what does a positive delta H value means? That means that a reaction is endothermic. It takes in heat. Okay, so we are basically having heat on the reactant side. We're taking in heat with an endothermic reaction. So what happens if we add heat to the system? It's going to want to proceed in the direction where heat is consumed. So when heat is added, the reaction will proceed in the endothermic direction to the right in this case. Again, it's going to take up that heat. The system will become darker, shaded brown, because NO2 concentrations would increase.